everyone. My name is Joshua Bostwick, a physics major at the University of Massachusetts Amherst, and today I'd like to talk to you about heat. Now, when you think of the word heat, what is the first thing that pops into your mind? Perhaps it's sitting next to a warm fireplace on a cold winter's night, or maybe it's the sun's rays at a day at the beach. Even though these are viable sources of heat, that's not what I'm going to be talking about in this video. I'm going to be talking about the heat that's being emitted by the device you're using to watch this video on. Now, what do I mean by this? Well, let me introduce to you something that nearly everyone in the world has: a cell phone. When we use cell phones, not only are we using them to make phone calls and send text messages, we're also using other applications on them, such as social media outlets and mobile games. However, you may notice that when you use your cell phone too much, it starts to feel a little bit warmer than it did before. That's because your phone is giving off its own sort of heat, called waste heat. Waste heat is produced by machines using energy in order for them to function. For instance, the lights in your room or the car that you drive all give off some sort of waste heat. With so many technologies producing waste heat, this creates an abundance of energy that can be harnessed for other electrical use. And the way this is being done at the moment is through thermoelectric devices and generators. Now, thermoelectricity is a conversion of heat to electricity, such as using your car exhaust in order to power your cell phone battery. Currently, strides are being made to capture heat emitted from electronics for other electrical use through thermoelectric generators. However, the main problem with the current generators on the market is that the materials that are being used for them have a low figure of merit, a dimensionless value that shows just how good a material is for thermoelectric use. For instance, the most common materials used for thermoelectrics are bismuth telluride and lead telluride, and these materials only give a figure of merit value of around 1. While this is currently the peak of thermoelectrics to this point, in order for them to be used for commercial purposes, the figure of merit has to increase to a value of around 3, which is nearly triple that of the best generators currently on the market. So how do we solve this problem? Well, my project hopes to increase this figure of merit by creating a process to use a hybrid of lead telluride and PEDOT, a large molecule polymer that has been mainly found in solar cells and solar panels, to make nanotubes, the size thinner than a strand of hair. By making these nanotubes, the goal will be to increase the seeback coefficient, which is a voltage that is produced by a difference in temperatures across a certain material. By increasing the seeback coefficient, this could allow for a larger figure of merit value, and therefore allow for thermoelectrics to be available for widespread use. If this were the case, we could power our electronics using any form of waste heat from any source. So who knows? Maybe down the road, the energy produced to show you this video may be used to power any type of electronic you have. Thanks for watching.